Welcome to Crocheting Through Medical History. I am Maria, and today I am not crocheting. I have been crocheting a lot this week, and I've got a lot of things done, which I'm excited to share about. I don't have any pictures to share right now, but I promise I've been doing things. Finally finished that blue sweater. I am almost done with my sister-in-law's bucket hat. It is like a hat now. It just needs a little brim. So, things are happening, I promise. But nothing really to share right now. Next week, I should have things to share. But it's been a long few weeks. Thank you for being patient with me, for being gone last week. Sorry if you weren't patient. That's not my problem. But I'm here. I'm not here with a real episode yet this week. But I'm here because I wanted to be here. So hopefully next week things will calm down. I will do some research. I'll have time for that. And we will have a real episode. But today we're just doing a fun little bonus episode about the invention of penicillin. This is one of the ones on my list that it's not like something I want to like research, but something I can find an article about. So if you have any topic suggestions for me to research or simply to find an article about to read, let me know. DM me, comment. And while you're there, you should follow me on Instagram, Maria Makes, and subscribe on YouTube, Maria Hegerman, and share with your friends. All right, let's go learn about penicillin. So, the introduction of penicillin in the 1940s, which began the era of antibiotics, has been recognized as one of the greatest advances in therapeutic medicine. The discovery of penicillin and the initial recognition of its therapeutic potential occurred in the United Kingdom, but due to World War II, the United States played the major role in developing large-scale production of the drug, thus making a life-saving substance in limited supply into a widely available medicine. Penicillin heralded the dawn of the antibiotic age. Before its introduction, there was no effective treatment for infections such as pneumonia, gonorrhea, or rheumatic fever. Hospitals were full of people with blood poisoning contracted from a cut or a scratch, and doctors could do little for them but wait and hope. Antibiotics are compounds produced by bacteria and fungi which are capable of killing or inhibiting competing microbial species. This phenomenon has long been known. It may explain why the ancient Egyptians had the practice of applying a poultice of moldy bread to infected wounds. But it was not until 1928 that penicillin, the first true antibiotic, was discovered by Alexander Fleming, professor of bacteriology at St. Mary's Hospital in London. I'm also drinking an Arizona tea. Not sponsored, just delicious. But is green tea with ginseng and honey, and I've been really into honey lately, so cheers. Returning from holiday on September 3rd, 1928, Fleming began to sort through Petri dishes. I just really wanted to say Petri right there. I know that's wrong. I wanted to do it, but I didn't. Petri dishes containing colonies of Staphylococcus. This is going really well. Let's try that again. Okay. Returning from holiday on September 3rd, 1928, Fleming began to sort through Petri dishes containing colonies of Staphylococcus, bacteria that cause boils, sore throats, and abscesses. He noticed something unusual on one dish. It was dotted with colonies, save for one area where a blob of mold was growing. The zone immediately around the mold, later identified as a rare strain of Penicillin notatum, was clear, as if the mold had secreted something that inhibited bacterial growth. Fleming found that his mold juice was capable of killing a wide range of harmful bacteria, such as Streptococcus, Meningococcus, and Diphtheria bacillus. He then set his assistants, Stuart Craddock and Frederick Ridley, the difficult task of isolating pure penicillin from the mold juice. Why does he keep saying mold juice? I'm not a fan of that. Okay, I think I can get over it. It may be done now. It proved to be very unstable, and they were only able to prepare solutions of crude material to work with. Fleming published his findings in the British Journal of Experimental Pathology in June 1929, with only a passing reference to penicillin's potential therapeutic benefits. Hello, Gimli. It's not time to start yelling. Please don't. No. I'm ignoring him. I can't ignore him. Okay. At this stage, it looked as if its main application would be isolating penicillin-insensitive bacteria from penicillin-sensitive bacteria in a mixed culture. This, at least, was of practical benefit to bacteriologists and kept interest in penicillin going. Others, including Harold Raystrick, professor of biochemistry at the London School of Hygiene and Tropical Medicine, tried to purify penicillin but failed. It was Howard Florey, Ernst Chain, and their colleagues at the Sir William Dunn School of Pathology at Oxford University who turned penicillin from a laboratory curiosity into a life-saving drug. Their work on the purification and chemistry of penicillin began in earnest in 1939, just when wartime conditions were beginning to make research especially difficult. To carry out a program of animal experiments and clinical trials, the team needed to process up to 200 liters a week of mold filtrate. They began growing it in a strange array of culture vessels such as baths, bedpans, milk churns, and food tins. Later, a customized fermentation vessel was designed for ease of removing and, to save space, renewing the broth beneath the surface of the mold. A team of penicillin girls was employed at €2. What? I'm really bad at European money, apparently. What does this mean? Oh, is it just $2? $2 Okay, so a team of penicillin girls was employed at $2 a week to inoculate and generally look after the fermentation. In effect, the Oxford laboratory was being turned into a penicillin factory. Gimli, stop playing with your loud toy. What are you even doing? Anyway. Meanwhile, biochemist Norman Heatley extracted penicillin from huge volumes of filtrate coming off the production line by extracting it into amyl acetate and then back into water using a countercurrent system. Edward Abraham, another biochemist who was employed to help step up production, then used the newly discovered technique of alumina column chromatography to remove impurities from the penicillin prior to clinical trials. In 1940, Florey carried out vital experiments showing that penicillin could protect mice against infection from deadly streptococci. Then, on February 12, 1941, a 43-year-old policeman, Albert Alexander, became the first recipient of the Oxford penicillin. He had scratched the side of his mouth while pruning roses and had developed a life-threatening infection with huge abscesses affecting his eyes, face, and lungs. Penicillin was injected, and within days he made a remarkable recovery. But supplies of the drug ran out, and he died a few days later. Oh, not where I thought that was going. Better results followed with other patients, though, and soon there were plans to make penicillin available for British troops in the battlefield. Wartime conditions made industrial production of penicillin difficult. A number of British companies, including Glaxo, now GlaxoSmithKline, and Kemble Bishop, a London firm later bought by Pfizer, took up the challenge. Substantial amounts of penicillin would be needed for the extensive clinical trials required to confirm the promise of the early results and to provide adequate supplies of the drug for therapeutic use if it did live up to its potential. Florey recognized that large-scale production of penicillin was probably out of the question in Britain, where the chemical industry was fully absorbed in the war effort. With the support of the Rockefeller Foundation, Florey and his colleague Norman Heatley traveled to the United States in the summer of 1941 to see if they could interest the American pharmaceutical industry in the effort to produce penicillin on a large scale. Yale physiologist John Fulton helped to put his British colleagues in touch with individuals who might be able to assist them in their goal. They were referred to Robert Thom of the Department of Agriculture, a foremost mycologist and authority in the penicillin mold, and eventually to the department's Northern Regional Research Laboratory, NRRL, in Peoria, Illinois, because of the expertise of its fermentation division. This contact proved to be crucial to the success of the project, as the NRRL was a key contributor of innovations that made large-scale production of penicillin possible. Orville May, director of the NRRL, agreed to have the laboratory undertake a vigorous program to increase penicillin yields under the direction of Robert Coghill, chief of the fermentation division. It was agreed that Heatley would remain in Peoria to share his expertise with his American colleagues. Within a few weeks, Andrew Moyer found that he could significantly increase the yield of penicillin by substituting lactose for the sucrose used by the Oxford team in their culture medium. Shortly thereafter, Moyer made the even more important discovery that the addition of corn steep liquor to the fermentation medium produced a tenfold increase in yield. Corn steep liquor was a byproduct of the corn wet milling process, and the NRRL, in an attempt to find a use for it, tried it in essentially all of its fermentation work. Later, the Peoria laboratory increased the yield of penicillin still further by the addition of penicillin precursors, such as phenylacetic acid, to the fermentation medium. It was recognized that the Oxford group's method of growing the mold on the surface of a nutrient medium was inefficient, and that growth in submerged culture would be a superior process. In submerged culture fermentation, the mold is grown in large tanks in a constantly agitated and aerated mixture, rather than just on the surface of the medium. Florey's penicillin culture, however, produced only traces of penicillin when grown in submerged culture. Under the direction of Kenneth Raper, staff at the NRRL screened various penicillin strains and found one that produced acceptable yields of penicillin in submerged culture. Soon, a global search was underway for better penicillin-producing strains, with soil samples being sent to the NRRL from around the world. Ironically, the most productive strain came from a moldy cantaloupe from Peoria Fruit Market. A more productive mutant of the so-called cantaloupe strain was produced with the use of X-rays at the Carnegie Institution. When this strain was exposed to ultraviolet radiation at the University of Wisconsin, its productivity was increased still further. While Norman Heatley remained in Peoria helping the NRRL staff to get penicillin work started, Howard Florey visited various pharmacological companies to try to interest them in the drug. Although Florey was disappointed in the immediate results of his trip, 3 of the companies, Merck, Squibb, and Lilly, had actually conducted some penicillin research before Florey's arrival, and Pfizer seemed on the verge of investigating the drug as well. At this time, however, the promise of penicillin was still based on only limited clinical trials. This is going so well. All into my mouth that time. Did you see that? See how good that was? I know how to drink out of a can. Florey next visited his old friend Alfred Newton Richards, then vice president for medical affairs at the University of Pennsylvania. More importantly, Richards was chair of the Committee on Medical Research, CMR, of the Office of Scientific Research and Development, OSRD. The OSRD had been created in June 1941 to assure that adequate attention was given to research on scientific and medical problems relating to national defense. Richards had a great respect for Florey and trusted his judgment about the potential value of penicillin. He approached the 4 drug firms that Florey indicated had shown some interest in the drug, Merck, Squibb, Lilly, and Pfizer, and informed them that they would be serving the national interest if they undertook penicillin production and that there might be support from the federal government. Richards convened a meeting in Washington, D.C. on October 8, 1941, to exchange information on company and government research and to plan a collaborative research program to expedite penicillin production. In addition to representatives of the CMR, the National Research Council, and the U.S. Department of Agriculture, participants included research directors Randolph T. Major of Merck, George A. Harrop of the Squibb Institute for Medical Research, Jasper Kane of Pfizer, and Y. Subborough of Lederle. The next CMR Penicillin Conference, held in New York in December, 10 days after Pearl Harbor and U.S. entry into the Second World War, was more decisive. At this meeting, which was attended by the heads of Merck, Squibb, Pfizer, and Lederle, as well as company research directors, Robert Coghill's report on the success at the NRRL with corn-steeped liquor was encouraging to the industry leaders present. As Coghill later recalled, George W. Merck, who had been pessimistic about the possibility of producing adequate quantities of penicillin given the constraints of available fermentation techniques and yields, immediately spoke up, saying that if these results could be confirmed in their laboratories, it was possible to produce the kilo of material for Florey, and industry would do it. It was agreed that although the companies would pursue their research activities independently, they would keep the CMR informed in developments, and the committee would make the information more widely available with the permission of the company involved, if they were deemed in the public interest. Although there was some concern that investments in the fermentation processes might be wasted if a commercially viable synthesis of penicillin were developed, other companies also began to show an interest in the drug. Some firms worked out collaborative agreements on their own, e.g. Merck and Squibb in February 1942, joined by Pfizer in September. Merck's pilot plant continued to produce several hundred liters of penicillin culture per week using both flasks and tray, and in December, Heatley joined the Merck research staff for several months, where he introduced the Oxford cup plate method of penicillin assay, which soon became a standard method industry-wide. By March 1942, enough penicillin had been produced under OSRD auspices to treat the first patient, Mrs. Ann Miller, in New Haven, Connecticut. A further 10 cases were treated by June 1942, all with penicillin supplied by Merck and Company Incorporated. Pharmaceutical and chemical companies played an especially important role in solving the problems inherent in scaling up submerged fermentation from a pilot plant to a manufacturing scale. As the scale of production increased, the scientists at Merck, Pfizer, Squibb, and other companies faced new engineering challenges. Pfizer's John L. Smith captured the complexity and uncertainty facing these companies during the scale-up process. The mold is as temperamental as an opera singer. The yields are too low, the isolation is difficult, the extraction is murder, the purification invites disaster, and the assay is unsatisfactory. Because penicillin needs air to grow, aerating the fermentation mixture in deep tanks presented a problem. When corn steep liquor was used as the culture medium, bubbling sterile air through the mixture caused severe foaming. Squibb solved this problem by introducing glycerol monoricinoate as an anti-foaming agent. Submerged fermentation also required the design of new cooling systems for the vats and new mixing technology to stir the penicillin mash efficiently. Lilly was particularly successful in making the mold synthesize new types of penicillin by feeding precursors of different structure. Once the fermentation was complete, recovery was also difficult. As much as 2/3 of the penicillin present could be lost during purification because of its instability and heat sensitivity. Extraction was done at a low temperature. Methods of freeze-drying under vacuum eventually gave the best results in purifying the penicillin to a stable, sterile, and usable final form. This article is so long. My voice was not prepared for this. It was not. Okay, 2 more sections. We're almost done. I don't even know where I am anymore. Okay. The steps of fermentation, recovery and purification, and packaging quickly yielded to the cooperative efforts of the chemical scientists and engineers working on pilot production of penicillin. On March 1st, 1944, Pfizer opened the first commercial plant for large-scale production of penicillin by submerged culture in Brooklyn, New York. Meanwhile, clinical studies in the military and civilian sectors were confirming the therapeutic promise of penicillin. The drug was shown to be effective in the treatment of a wide variety of infections, including streptococcal, staphylococcal, and gonococcal infections. The United States Army established the value of penicillin in the treatment of surgical and wound infections. Clinical studies also demonstrated its effectiveness against syphilis, and by 1944, it was the primary treatment for this disease in the armed forces of Britain and the United States. The increasingly obvious value of penicillin in the war effort led the War Production Board, WPB, in 1943 to take responsibility for increased production of the drug. The WPB investigated more than 175 companies before selecting 21 to participate in a penicillin program under the direction of Albert Elder, in addition to Lilly, Merck, Pfizer, and Squibb. Abbott Laboratories, which had also been among the major producers of clinical supplies of penicillin to mid-1943, was one of the first companies to begin large-scale production. These firms received top priority on construction materials and other supplies necessary to meet the production goals. The WPB controlled the disposition of all the penicillin produced. One of the major goals was to have an adequate supply of the drug on hand for the proposed D-Day invasion of Europe. Feelings of wartime patriotism greatly stimulated work on penicillin in the United Kingdom and the United States. For example, Albert Elder wrote to manufacturers in 1943, quote, "You are urged to impress upon every worker in your plant that penicillin produced today will be saving the life of someone in a few days or curing the disease of someone now incapacitated. Put up slogans in your plant notices, place notices in pay envelopes. Create an enthusiasm for the job down to the lowest worker in your plant," unquote. As publicity concerning this new miracle drug began to reach the public, the demand for penicillin increased, but supplies at first were limited and priority was given to military use. Dr. Chester Kiefer of Boston, chairman of the National Research Council's Committee on Chemotherapy, had the unenviable task of rationing supplies of the drug for civilian use. Kiefer had to restrict the use of the drug to cases where other methods of treatment had failed. Part of his job was also to collect detailed clinical information about the use of the drug so that the fuller understanding of its potential and limitations could be developed. Not surprisingly, Kiefer was besieged with pleas for penicillin. A newspaper account in the New York Herald Tribune for October 17, 1943, stated, quote, "Many laymen, husbands, wives, parents, brothers, sisters, friends, beg Dr. Kiefer for penicillin. In every case, the petitioner is told to arrange that a full dossier on the patient's condition be sent by the doctor in charge. When this is received, the decision is made on a medical, not an emotional basis," unquote. Fortunately, penicillin production began to increase dramatically in early 1944. Production of the drug in the United States jumped from 21 billion units in 1943 to 1,663 billion units in 1944, to more than 6.8 trillion units in 1945, and manufacturing techniques had changed in scale and sophistication from 1-liter flasks with less than 1% yield to 10,000-gallon tanks at 80 to 90% yield. The American government was eventually able to remove all restrictions on its availability, and as of March 15, 1945, penicillin was distributed through the usual channels and was available to the consumer in his or her corner pharmacy. By 1949, the annual production of penicillin in the United States was 133,229 billion units, and the price has dropped from $20 per 100,000 units in 1943 to less than 10 cents. Most British companies moved over to the deep tank fermentation production of penicillin, pioneered in the United States after the end of the war to meet civilian needs. In the United Kingdom, penicillin first went on sale to the general public as a prescription-only drug on June 1st, 1946. In Britain, Chain and Abraham continued to work on the structure of the penicillin molecule, aided by the X-ray crystallographic work of Dorothy Hodgkin, also at Oxford. The unique feature of the structure, which was finally established in 1945, is the 4-membered highly labile beta-lactam ring fused to a thiazolidine ring. In the same year, Alexander Fleming, Howard Florey, and Ernst Chain were awarded the Nobel Prize for their penicillin research. The cooperative efforts of American chemists, chemical engineers, microbiologists, mycologists, government agencies, and chemical and pharmaceutical manufacturers were equal to the challenge posed by Howard Florey and Norman Heatley in 1941. As Florey observed in 1949, quote, "Too high a tribute cannot be paid to the enterprise and energy with which the American manufacturing firms tackled the large-scale production of the drug. Had it not been for their efforts, there would certainly not have been sufficient penicillin by D-Day in Normandy in 1944 to treat all severe casualties, both British and American," unquote. One more section. The American Chemical Society and Royal Society of Chemistry designated the discovery and development of penicillin an international historical chemical landmark on November 19, 1999, at the Alexander Fleming Laboratory Museum in London, UK. The plaque commemorating the events reads, quote, "In 1928 at St. Mary's Hospital, London, Alexander Fleming discovered penicillin. This discovery led to the introduction of antibiotics that greatly reduced the number of deaths from infection. Howard W. Florey at the University of Oxford, working with Ernst B. Chain, Norman G. Heatley, and Edward P. Abraham, successfully took penicillin from the laboratory to the clinic as a medical treatment in 1941. The large-scale development of penicillin was undertaken in the United States of America during 1939 to 1945 World War, led by scientists and engineers at the Northern Regional Research Laboratory of the U.S. Department of Agriculture, Abbott Laboratories, Leader Lee Laboratories, Merck and Company, Inc., Pfizer and Company, Inc., and E.R. Squibb and Sons. The discovery and development of penicillin was a milestone in 20th century pharmaceutical chemistry, unquote. Plaques were also given to commemorate the contributors of the U.S. Department of Agriculture National Center for Agricultural Utilization Research and 5 American pharmaceutical companies, including Abbott Laboratories, Leader Lee Laboratories, now Pfizer Inc., Merck and Company Inc., Pfizer and Company Inc., now Pfizer Inc., and E.R. Squibb and Sons, now Bristol Myers Squibb Company. That's a lot of names. This article was adapted for the internet from The Discovery and Development of Penicillin, 1928 to 1945, produced by the American Chemical Society and the Royal Society of Chemistry in 1999. This article is on acs.org, from ACS Chemistry for Life. So yes, thank you to ACS for this article. My voice is crying. This has been really long after not recording for 2 weeks. I hope you enjoy. Raise your hand if you have a penicillin allergy. I don't. But you should sound off in the comments if you do. Sorry that you're allergic to penicillin. I'm gonna go to bed, probably. I will keep you updated on Allie's bucket hat. It is almost done. She is leaving in 4 days. So I have 4 days to finish this. I believe in myself. I'm almost done. I even sewed in all the ends and everything. Look how nice and clean this is. Look, this is the inside. It looks so nice. It's almost done. Just need a rim. I will be probably posting a lot next week because I think that is when I will have a lot of the pictures ready to go from the things I've made this week, which I don't feel like explaining because I simply cannot talk. My throat is crying. Thank you for listening or watching. Like, subscribe, share with your friends. Follow me on Instagram, Maria Makes. Follow me on whatever podcast platform you may be listening on. If you have topic suggestions, let me know. If you have a condition and are willing to talk to me about it, let me know that too. I'm always interested in talking to people with conditions that I don't know a ton about. So, yeah, we got exciting things coming up, I promise. Thank you for being patient with me again. I will be back next week with a real episode. So join me next week. Stay safe, stay healthy, and I will see you next week. Bye.